This is the third video in a series on Hopital's rule. Let's go solve some limits. Now today, the limits we solve don't have this typical Hopital form. We expect 0 over 0 or infinity over infinity. We know Hopital works well on those kind of limits, but what about some of these other indeterminate forms? And these are interesting, I think. You know, all the way through your elementary mathematics, you learned about powers and eventually encountered the 0 power of a number equaling 1. But then they told you 0 to the 0 power is undefined. And then when you do limits with this, it's indeterminate. You can get different answers. Sometimes they come out to 1, sometimes they don't. We'll explore that today. And then how about this one? 1 to the infinity power. That doesn't really mean 1 times 1 times 1 times 1 with an infinite number of factors. The base in this is going to be an expression that approaches 1 just as the exponent becomes unboundedly large. 1 to the infinity. We'll look at one of those today too. And I'm quite sure we'll get infinity minus infinity at some point. Anyway, enough talk. Let's go after it here. What's this first one? As x goes to 0, clearly the base has a value of 0 or approaches 0, as does the exponent. This is a 0 to the 0 power in form. Okay, to go about solving something like this, what we do is we just make the assumption that there is a limit in the first place, and we give it a name, like L. So we say L equals the limit as x approaches 0 from the right of 2x raised to the x squared power. And then we take a natural log on both sides. So I guess I'll go ahead and do that here since it fits. And then we let that continuous log function go inside the limit. And that looks like this. Limit as x approaches 0 from the right of the log of 2x to the x squared power. All right, we have log properties that tell us when you take the log of a power, you can just take the log of the base and use the exponent as a multiplier of the log. We call that bringing the exponent down. Now it looks like this. Limit as x approaches 0 from the right of x squared times the natural log of 2x. Now let's stop and see what limit form we have now. It can't be L'Hopital because it doesn't look like a ratio, like one of these. As x goes to 0, x squared goes to 0. What about natural log? You may be familiar with this graph, but the natural log graph looks something like this, and it doesn't make that big of a difference that it's multiplied by 2 inside here. Natural log graph looks something like this. It's got a domain of only positive numbers, and as x approaches 0 from the right, the natural log graph approaches negative infinity. So the form I have right now is 0 times negative infinity. We can make this into a L'Hopital form by just bringing x squared under here and using a negative exponent. That looks like this. Limit as x approaches 0 from the right of natural log 2x over x to the negative 2 power. What form do we have now? Well, I already explained that this upper expression in the numerator is approaching negative infinity. Okay, it turns out that this expression is approaching positive infinity, and I'll explain that here. Remember, x to the negative 2 equals 1 over x squared. Okay, the graph of 1 over x squared is all positive. It looks a little bit like 1 over x in the first quadrant, and that's all we really care about for this problem. As x approaches 0 from the right, 1 over x squared goes to positive infinity. So my form now is negative infinity over positive infinity, and that is a L'Hopital form. So let's take some derivatives. Let's apply L'Hopital's rule. The derivative of natural log 2x is 1 over 2x, but then you have to multiply by 2 because of the chain rule. So you end up with the following derivative in the numerator. It's just 1 over x. And the derivative of x to the negative 2 power is negative 2x to the negative 3 power. So we do some simplifying, and I'll do that over to the right here. This is 1 over x divided by negative 2 over x cubed. And of course, you can, instead of dividing by negative 2 over x cubed, you can multiply by x cubed over negative 2 like this, and you end up with x squared over negative 2. So we're almost done. This is the limit as x approaches 0 from the right of x squared over negative 2. And that's just the limit of a polynomial. Plug in the 0, and you'll get your answer. Now you have to be a little bit careful, because when you get to the end and you see a 0, you're not quite done. That 0 is equal to all of these limits back here, which are equal to the natural log of the answer we want. So you can write this equation now. Natural log of L equals 0. And since these are equal things, they can sit on equal bases to make equal powers like this. And I did that because the base exponential and the natural log are inverse functions. They cancel, and I end up with L equals e to the 0 power. E to the 0 power is 1, and now you can say you're finished. The answer is 1. What do we start with? We started with a limit that had the form 0 to the 0 power. And we didn't skip any steps. We're very pedantic about this, and we got down to the end and we came up with 0 to the 0 power is not equal to 1, but in the limit it is 1 for this problem. Does it always come out to 1? 0 to the 0 power? Does it always come out to 1? No, it's indeterminate, which means it can come out to lots of different things. This next example is a lot of fun. Hey Jenny, pick your favorite number.
3.
Okay. Been married almost 24 years, and I just learned my wife's favorite number is 3. This limit has the form 0 to the 0 power, which I'll explain again. And if we just put a 3 in here where that a is, I can make this come out to 3 in the limit. And how are we going to do that? Well, first of all, is it really 0 to the 0? Yeah. If x goes to 0, the base goes to 0. Clearly, natural log of 3 is a number just a little bit bigger than 1. But the natural log of, as 0 goes to the right, the natural log goes to negative infinity as explained. So approximately 1 over negative infinity is 0. This is a 0 to the 0 problem. We're going to solve this almost like we did the last one, except I'm not going to have the need to, well, let's just get after it. Let's assume there's an answer. And I'm here to tell you I don't think it's going to be 1. I think it's going to be 3. Let's see if I'm right. Set L equal to the limit as x goes to 0 from the right of x raised to the natural log of a over the natural log of x. And then take the natural log on both sides. And just like in the last problem, we're going to let the natural log go inside the limit. So that looks like this. A lot of these problems have the first same 3 steps. So if you can come up with a way to shortcut any of these steps, you should. So this is natural log of x raised to the natural log of a over natural log of x power. And similar to the previous problem, I'm going to use the property where when you take the natural log of a power, you can just take the natural log of the base and then use the exponent as a multiplier of the log. Very, very important log property. But what would that look like? Well, that would look like the natural log of x, okay, natural log of the base, multiplied by what used to be this exponent. Now, this problem was cleverly designed to get these natural logs to cancel at this point, and they do. And because a is the number 3 in this case, or any number you want, this is a constant, and the limit of the constant is the constant, and so we get natural log of a. Okay, now that's not the answer to the problem. The natural log of a is equal to the natural log of the limit of the problem in the first place. So if I bring this down here, you barely even really need to exponentiate both sides. Equal logs with equal bases have equal arguments, and therefore the limit of this problem is a, which today is my wife's favorite number, 3. All right, here's another problem. It's not 0 to the 0. It's one of the other indeterminate forms that you saw in that table. We're taking the limit as x goes to infinity of 1 plus pi over x all raised to the x power. Now this is related to a limit I think you've seen before. Well, you should have. It's the limit as x approaches infinity of 1 plus 1 over x raised to the x power. You may recognize that as a limit that ends up equaling e. But both of these limits have something in common. What is that? Well, if you go in here and you divide pi by infinity, you of course are getting 0, and 1 plus 0 is 1. So the base has a limit of 1, and the exponent has a limit of infinity. The form of this limit is 1 to the infinity power. We saw that in the table. That's an indeterminate form. Let's go ahead and see if we can force it into being some kind of L'Hopital form. Okay, the strategy to this is very similar to the previous problems. We assume it exists, we let it equal to L, and we take the limit as x approaches infinity, just write it down again, and then go ahead and take a natural log on both sides. Similar to the previous problems, let's let that continuous natural log function go inside of the limit, like this. Similar to all the previous problems today, let's let this exponent come down and multiply the log. That would look like this. Before we get too carried away, let's stop and evaluate the form of this limit. We'll have a product of two things. Okay? X is going to infinity, so this is clearly infinity. Multiplied by what? All right, be careful. Pi divided by infinity should be 0. Added to 1 is 1. So this inside the log here is approaching 1, and the natural log of 1 is 0. So I have I have infinity times 0 here as a form. To make this look like a L'Hopital form, what we're going to do is put this x down here as a 1 over x. That looks like this. So we'll have in the numerator natural log of 1 plus pi over x. And in the denominator, we'll have 1 over x. Now, turns out we have a L'Hopital form. Why? Well, I already explained why this has a limit as x approaches infinity of 0. This is 1 over infinity, so that's also 0. And so now we can apply L'Hopital's rule. And that means what? That means taking derivatives in both the numerator and denominator. Okay, what's natural log's derivative? It's 1 over whatever's inside of the log. But if what's in the log is not just x, you'll have to multiply by a chain rule factor. The chain rule factor, the second factor, I should say, is the derivative of this interior function. And that turns out to be 0 here plus negative pi x to the negative 2. Or how about just negative pi over x squared? The denominator's derivative is a little less complicated. It's just the derivative of that, which turns out to be negative 1 over x squared. Now it looks like we can do some canceling. Cancel the x squareds, cancel the negatives, multiply pi by 1. And running out of space here, but that's good. We're getting close to the end of this problem. This ends up being the limit as x goes to infinity of pi over 1 plus pi over x. Now, as x goes to infinity, pi over x goes to 0. 0 plus 1 is 1. Pi divided by 1 is pi. Is that the answer? No, you've seen this too many times today. Pi is equal to this limit, is equal to this limit, equal to natural log of L. L is the thing we're trying to figure out. So, what I have is natural log of L, our answer is pi, and if you just exponentiate both sides raised to this power and this power of e, you end up with L equals e to the pi. So, I hope you're convinced now. 1 raised to the infinity power in a limit problem, that form can come out to something very different than 1. In this case, it was e to the pi power. Moving on. All right, here's a problem that has the form infinity minus infinity, right? Infinity here. Natural log of infinity is also infinity. And infinity minus infinity, I promise you, has nothing to do with L'Hopital's rule, unless you can cleverly compel it to have something to do with L'Hopital's rule. The trick on this problem is to rewrite this x as x equals the natural log of e to the x, which is certainly true. But then what you'll have in here is a log minus a log, and we have a property that helps us with that. So this is the limit as x approaches infinity of natural log e to the x minus natural log of x. And a log minus a log, of course, is a single log of a quotient of the argument. So this is limit as x approaches infinity of the natural log of e to the x over x. Okay, in a previous video, I explained a quick way to figure this out. But I'm going to go ahead and, instead of using order of magnitude, I'm going to go ahead and just use L'Hopital's rule, because this right now has an infinity over infinity form inside this log. And I guess I should bring the limit inside the log. So let's do two things at once. Let's go bring the limit inside the log. And then let's take the derivatives of both of these, since this is a L'Hopital form. And I get this. And evaluating at infinity, the numerator goes infinite, the denominator is a constant, so I have infinity divided by 1 is infinity. And to finish this problem, I just have to take the natural log of infinity, which of course is infinity. Now, is that the answer to the problem? It is. We're done. But I thought I'd make a quick little sketch to try to illustrate just what exactly this is saying. Okay, you have these two expressions. X is going to infinity. So both of these, think of these as functions or calculations for y, are going infinite also. But what we just discovered is that the difference between these two things is also infinite. Take a look at a graph, and I think it'll make sense. Here's a graph of y equals x. Okay. So as x goes to infinity, pretty clearly y goes to infinity. And here's a graph of natural log. It doesn't appear to be getting very infinite, but trust me, it gets there. You can make the argument. It just gets there more slowly, and that's kind of the point. So this x minus natural log x thing that you see over here is quite literally the difference between these two curves, the vertical distance. And that's growing. And what we just discovered is it is growing without bound. So that difference goes to infinity. Okay, now we have one more problem here that I think is kind of fun, and I'm going to do it a little bit faster. First of all, what form is it? It's 1 raised to, well, let's see, if you put 1 in here, 2 times 1 is 2 minus 2 is 0. Can you divide 1 by 0? No, but this is a limit as x approaches 1 from the right, so this is a little bit bigger than 2. So we have 1 over some number that is just barely bigger than 0 and positive, which means this exponent is going to infinity. So this time our form is 1 to the infinity power. And we're going to do these problems, this last problem like we did all the others. We're going to let L equal the answer, just assume there is an answer. And then we're going to take the natural log of both sides. And I'm going to do it 2 or 3 steps at once here. If I take a log on the left and I take a log on the right, I can let the log go inside the limit, so it'll be here, and then I'll have the log of a power, so I can just take the log of the base, and then I can take the exponent down in front of the log. Well, you've seen this enough today, maybe you can follow this. So again, let the log go inside the limit, but instead of taking the log of this whole power, take the exponent and bring it down in front of the power like this. And if you want, you can write this as a quotient like this. And then you can try to evaluate to see what form of limit you have. Well, as x approaches 1 from the right, the natural log approaches 0. As x approaches 1 from the right, 2x minus 2 approaches 0. So it's a 0 over 0 form, which means, of course, we can employ L'Hopital's rule. And we'll be just about done. On top, the derivative is 1 over x, and on the bottom, the derivative is 2. Plugging in a 1 into this expression gives us 1/2. And is that the answer to the problem, 1/2? No, 1/2 is equal to the natural log of our answer. So, almost done. Natural log of where we're going to end up is equal to 1/2. These equal numbers can act as equal exponents over equal bases like this. And when you're done, the exponential and the log cancel, and you end up with L equals e to the 1/2 power, or if you prefer, the square root of e. And we're done. I hope you enjoyed. My name's Eric. Have a good day.